An essential task in data science is explaining where our data is coming from, meaning finding out the model of the world that the data is coming from, specifically finding the statistical behavior of the world, right? So, like, let's say we have a coin, and I know that this coin is not a fair coin. The probability of heads is different from um, zero point 0.5, and we are given this coin, and all we have this coin, and look at the coin and collect data, and to understand how this probability of heads is, um, the easiest solution is to go ahead and do several throws of this coin tosses and count the number of heads by and divide it by the number of um, experiments. So this has been the most intuitive and available way of calculating the simplest statistics behind the data. Um, but in this video, I will be showing that this counting and dividing is actually maximum likelihood estimation. And of course, for the first time right now, I will be describing what likelihood is and what is the word maximum here next to likelihood. What are we doing with the likelihood, and why actually are we counting actually? Like what is the science behind this very simplistic approach, and what can we do if it is a little bit more complicated than just counting? So here we go. Let me open up my notebook. So the again, I will take it a little bit a few steps back. I will take it. Let me put the title. So our title is maximum likelihood estimation. And again, so this is a uh, very long title, a very involved. So maximum likelihood estimation of what? Any kind of model, right? But I will start simple. I will start with what we have started in elementary school, and if not earlier, with the simple coin toss example. Say we have this coin, one part of his head, and the other is tails. And we know in the very beginning, we started with this coin toss, um, knowing that coin is a fair coin, right? We know the probability of head is when we start is half, and we start probability of tail is half. So please hang on with me. I know I started from the Big Bang, like when everything was dust, when nothing existed, right? But I will get to why we count. And since we have this, we were able to calculate a probability given this model, given this fair coin assumption. We were able to calculate some observation. I'm going to use this capital chi, and I'm going to call it observation. Another name for this is in data science, we call it data or data sets, right? So in my data, which is a plural word actually. So let's say my data is head, tail, head. So I observe this data, and given this model, this assumption of fairness, I can calculate the probability of my X. So now at this point, I would like to call this thing my model. I'm going to put a capital M here, M for model, and this is the model is I can call it the fair coin assumption. So this might not be the case always, and I'm going to now calculate the probability of observing what I have observed, and I'm going to condition on this model, right? So that's the terminology wise, it might look simple, it might look um, new, but it's actually uh, the same thing, right? So I'm observing the probability of head, 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 tail, tail, head, right? So, and again, this is still conditioned on the model. This condition part, this is the new part, right? So this didn't exist in elementary school. So this is new. But this actually always existed, except we didn't write this part. And now I know that I can write this as probability of head times probability of head times probability of head, probability of tail, probability of tail. God, why did I took such a long sequence? I could have proved my point with a very short one. But anyway, another tail and probability of head. Why did I write all of them to be as a multiplication? The underlying assumption is each coin toss is independent. So if my coin tosses actually harmed the coin in my hand, then they wouldn't be independent. Dependent. And I know since my calculation, I know I'm dealing with a fair coin. This is 1/2. This is also 1/2. Everything is 1/2. This is also 1/2. This is also 1/2. This is also 1/2. So this is 1, 2, 3, 4, 5, 6, 1/64, right? So I know the probability of observing what I have observed is obtained like that. So now I can introduce the terminology. So this thing is called likelihood. This thing, probability of observing what I have observed given the data, is called likelihood. Let me go ahead and write it nicely, because this is half of the title of our not half, maximum likelihood estimation, 1/3 of the title. So one good definition of likelihood would be probability of observing what I have observed, meaning the data, given the model, or given the, I'm gonna use another word here, assumed model, because models are always assumed, right? We assume that it is fair. And now let's make it a little bit different. Let's assume that my coin is not fair. That's like, let's say now my model 2 is, let's assume that my model 2 probability of head is 0.6. It's a little bit weird. And my probability of tail becomes 0.4. And I'm again ignoring the width. So like, again, I get my data. I observe, again, this time head, head, tail, 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 head. And then I tell my colleagues who observe this sequence with me. I say, well, this is the model. This is the coin that we're dealing with. And then my colleagues take a look at this data and say, are you sure? Like looking at this data, what is the likelihood really of this model? Like this model being the truth, like this model explaining what we have just observed. What is the likelihood of that? So all of a sudden, this terminology, the definition that I provided up top, makes more sense, right? And again, I can say, well, let's calculate, because likelihood is something that we can calculate. So we can calculate probability of x given m2 or chi given m2 is equal to, again, I'm not going to write down the assumption of independence. Now I'm going to write how many heads. There are like 1, 2, 3 heads, so 0.6 to the 3, and 1, 2, 3, 4 tails times 0.4 times 4. So this is the likelihood. And now you can see that the likelihood of some other model assumption, meaning a fair coin, or a coin maybe that favors tails more than fair, might have a higher likelihood. So now I'm trying to have an understanding of what would be the model that describes the, the data, that explains the data better than other models. So now I'm making this probability a parameter, right? So like there might be a model that explains my data better than others. So I can now talk about a model. So this model, and this model, now I can make this model a parametric model, right? So I don't need to try every single model. I don't need to try every single rational number that could give me a probability of heads. I can make it a probability. I can make it a parameter, right, of theta. So with this model, I can say the probability of head can become my theta, and then probability of tail then becomes 1 minus this theta, since their summation have to equal to 1. So now all of a sudden I have a model that I can write the probability, right? So I can now, instead of writing model theta, all I'm trying to find the theta. Then the theta is a descriptive of the model that I'm trying to find, right? So now I can talk about the probability of the data given theta. So that's my likelihood. And you see that this likelihood is now a function. It's now a function of my theta, which is theta to 3 and 1 minus theta to 4, right? So now I have some function, theta to 3, 1 minus theta to 4. And now another step forward, now I'm generalizing. So like remember the experiment of understanding theta with the coin that I'm holding in my hand. I can go ahead and throw it away, toss it however many times that I need. So let's say I toss the coin n times, and k of them lands heads. So then what? So this is my big question. What is the maximum likelihood estimation of theta for this coin? In other words, what might be the best model for this coin that I'm talking about? How is my coin? I'm asking actually. So this is a very like math savvy question that looks like math savvy. But remember, all I'm trying to do is to find the best model. So the probability, so in this scenario, I know my likelihood is defined as probability of chi, or my data, given theta, right? And I know since my theta, my x, again, this x is nothing but x1, x2, x3, yada yada yada, and I cost them n times. So I know since they are my likelihood, I'm gonna use this script L to describe my likelihood. So I know since they're independent, I can write it as I equals 1 to capital N probability of x of I given theta. So that's simple. And with my model in hand, now I have a likelihood which is a function, right? So my likelihood is then something like theta to, I know, k of them was head. So my probability of head was theta. So it should be theta to the k. And for the others, they happened with probability of 1 minus theta. So it should be n minus k. So that's my likelihood. So given this function, my task is to find the best theta, right? So this theta, I'm going to call it theta star, and I'm going to write here maximum likelihood estimation. The best theta that my data presents to me should be some theta that's, uh, since this is a function, that maximizes this, right? So I would like to maximize the likelihood, and the best theta should be at the argmax of this, right? So that's one great rule of maximum likelihood estimation. So maximum likelihood estimation. So I'm reaching, I'm getting there almost. So I would like to find a maximum likelihood. So I have a function. Um, from calculus, I know if I were to find the argument of that function that maximizes this function, now my arguments are theta, I know that I would like have to take the derivative and make it equal to 0, right? So So my theta star maximum likelihood should be, or I shouldn't say equal, should be at d L over d theta equal to 0, right? So like my maximum likelihood estimation should be here. But taking the derivative of this is a little bit difficult. And as we move forward with some other probability functions, you will see that they always follow some exponential family of functions. And with exponential family of functions, taking derivatives are not so nice. But we know we can take the logarithm of the likelihood, and we can also say my maximum likelihood is also some theta that maximizes not only the likelihood, but also the log likelihood, because logarithm is a monotonic function. If some number maximizes some function f, the same number maximizes log of x, log of f of x, right? Because log is a monotonic function. So I can also write my theta star Emily is also at argmax of log of L. And this guy has log of L. it's so frequently visited that we have log likelihood is a term. Like we don't say log of likelihood, log likelihood, or sometimes we use it LL. LL is also a term. So I know that I can then I can say my whoops, why did I go to blue all of a sudden? So I can write my theta star Emily is at my d log of my function, which is theta to the k 1 minus theta to n minus k, close parentheses, d theta equal to 0. Okay, this is, I think, as complicated as it gets, the good news. So it is going, from this point on, it's going to be simpler, I promise. So the one beautiful thing about the log function is that it's like a solvent. It makes the multiplications summations, exponentiations multiplications. Everything becomes a simpler version of themselves, right? So then I have to write. So I know. Um, so so this is going to be summation, right? So exponentiations become summations. Sorry, exponentiations become multiplications. So k log theta and plus and minus k log 1 minus theta. So that's the log of this up term. And I would like to find d over d theta evaluated at some theta star MLE. That's going to be equal to 0. I know. Well, I guess it looks a little bit more crowded than before, but you see how I went. I just took the log, right? Now let's go ahead and take the derivative, shall we? So the derivative of um, log theta is 1 over theta. So k over theta plus and minus k over log 1 minus theta is again 1 minus theta, but now I need to incorporate the minus theta part. The derivative of the 1 minus theta is minus 1. So when I incorporate that, this is becoming a calculus class, which I don't intend to, but all I did is I took the derivative. Now let's do the evaluated at parts, just like put a star on top of the thetas that I see. So these are my MLEs equal to 0. Now um, I'm back from calculus to algebra. I'm going to solve this theta, right? So let's go. So I make them, I distribute the denominator. So k times 1 minus theta star. I feel lazy. I'm not going to write the MLEs. 1 minus theta minus theta star and minus k. The numerator is theta times 1 minus theta. I don't need to write it. I know theta exists, and theta is non-zero. Therefore, the denominator cannot be 0. Hopefully, because I have observed something, right? So n is not equal to k. Therefore, 1 minus theta also exists. So let's make it k minus k theta star minus theta star n plus k theta star is equal to 0. When I see this, I'm so happy I can eliminate these guys. So I see that k equals to, or let's send the k to the other side. So theta star n is equal to k, and my theta star, therefore, let me write this here, bigger, my theta star, now I can write MLE is equal to k over n. Duh. Let's write the duh. Because like that was the thing that we were trying to show, right? So this was Like I counted k of them. I know I throw, let's say 1,000, and 850 of them became heads. Then I can say, well, it's 0.85, right? My best estimate. So this, my dear friends, is the maximum likelihood estimate of the binomial parameter theta.